All right, let's take a look at the derivatives of periodic functions, namely sine and cosine. Okay, now you know that the derivative of a function is essentially the instantaneous rate of change of that function at any given point. Okay, and the instantaneous rate of change of a function is essentially the slope. So here I have the graphs of sine and cosine, and in order to get an idea of what the derivatives are, we can sketch a graph of the derivative by evaluating the slopes at any point on a function, on the function. Okay, so that's what I want to do first, is just give you, we're just going to sketch a graph of the derivative, and then I'll give you the actual derivatives of sine and cosine. All right, so I'm going to start with the sine function. Now, I have the sine and the cosine function here side by side, and the blank graphs down here below to sketch the derivatives. So I'm going to zoom out a little bit so that we can see both at the same time. So let me zoom out. Let's see, is that going to work? Well, maybe I need to zoom out again. All right. Well, all right, so it's off to the side now, but let's take a look at this. See what the slope is. See what the derivatives are. Okay, so let's start with the sine. Now you can see here as we go from left to right on the x-axis, the sine is increasing. It's increasing, so the slope is positive. All right, so I'm just going to put little positive signs here. So the slope is positive. Now when I go to graph the derivative, that means that the derivative is going to be above the x-axis, right? Because it's positive. The derivative is positive for those x values. Okay. Up here at this point, right here, we have, we're changing. We're positive, and then you can see here we're going down, right? We're decreasing. The function is decreasing here from about, what is that, negative 3 pi over 2 to about negative pi over 2. Okay, so from negative 3 pi over 2 to negative pi over 2, right? The graph of our derivative is going to be below the x-axis. And right here at this point where it turns around from being increasing to decreasing, the slope is 0. So at this point, the derivative is equal to 0, which means it's going to cross the x-axis at that point. Okay, so let's actually, it's probably easiest just to identify the points where the derivative is 0. And those will be our x-intercepts for the derivative. Okay, so up here, we're going from increasing to decreasing. Slope is 0. So at 3 pi over 2, we're going to cross the x-axis. That will correspond to that point on the derivative, right? The derivative is 0 at that point. It's increasing when we are less than negative 3 pi over 2. And then when we're greater than 3 pi over 2, it's decreasing. So we're going to be above the x-axis. So that's kind of like we're going to be here. And then we'll switch to going below the x-axis. Okay. Now let's look at another point here. Right here as well, we've got the derivative is equal to 0. Okay. So again, at negative pi over 2, just right here, we're going to cross the x-axis. Okay. And then, but now we're going from, at this point, we're going from decreasing to increasing. So over here, our slope is positive. You can see we're increasing as we go, as x increases. Okay. So we have an increasing function between negative pi over 2, and it looks like it switches around here at pi over 2. Okay. So in this case, we're going from decreasing to increasing. So it's going to look something like that, going through that point. All right, so let's continue identifying those points where the slope is 0. So here we're going from increasing to decreasing, right? The slope is negative over here. And looks like that's about pi over 2. So again, we're going to cross the x-axis. The derivative is going to cross the x-axis here, and we're going from positive to negative, right? The slope is going from positive to negative. Okay, and then we have another point over here where the derivative is 0. Oops, dx equals 0. dy dx equals 0. Okay, and this looks like it's 3 pi over 2. So we'll have another point here. And in this case, we're going from decreasing to increasing, right? Because this slope over here is positive. Okay, so we've got a little bit of an idea here of what's happening. Now we just need to kind of connect these up. And it's difficult to tell what the actual slopes are from this graph. You know, I've got two different scales. Here I'm going from negative 2 pi to pi. I should use my mouse because I think it actually registers better. Okay, so it's going, you know, from negative 2 pi to pi. You know, so the scale is weird, so it's hard to tell what the actual slope is. But I'm just going to sketch this. And I will tell you that the slope maxes out here at 1. So if I draw this, try and draw it relatively neatly. And down here, it goes to negative 1. So let's see if I can draw this. And then it goes back up to positive 1. Okay, so I'm doing the best I can with drawing this, but sketching what this graph looks like, oof, not very good. Coming down here to negative 1, and coming back up. Okay, so there's a sketch. It's a sketch, so it doesn't have to be perfect. But I want to give you that idea of the shape of the derivative. Now that should look familiar, right? That looks a lot like this graph over here, right? This graph of cosine. And it is. The derivative of the sine is the cosine. So I will write that down here. Dy dx equals cosine of x. Okay? All right. Now I'm going to have you pause the video and try the cosine yourself. Identify where the slope is 0, where it's increasing, where it's decreasing, and sketch a graph of the derivative of cosine. And you can then, once you've got that, you can come back and I will show it to you. All right, so I've sketched the graph of the derivative of the cosine function. So you can see between negative 2 pi to negative pi, the slope is negative, so we're below the x-axis. We've got derivative of 0, at the points where it's changing direction, right? So at negative 2 pi, negative pi, 0, pi, and 2 pi, you can see where I've drawn the x-intercepts because the derivative is 0 at those points. That means it's changing from either increasing to decreasing or decreasing to increasing at those points. And then if the slope is decreasing, then we're below the x-axis, right? So down here, here the slope is decreasing, okay? And our graph of the derivative is below the x-axis. Here the slope is increasing from negative pi to 0, so our graph is above the x-axis. And here the slope is decreasing, so the graph of the derivative is below the x-axis. And so on, right? Here we're increasing, the slope is increasing, or sorry, the function is increasing, and the slope, which is the derivative, is above the x-axis. Okay, so there's a graph of the derivative of cosine. Now that should also look familiar, right? Now, it sort of looks like sine, but it's flipped over. And the derivative of the cosine is, let me see if I can, actually I think I could, yeah. I think I'm going to go back to my full screen view here. So let's see, I'm going to increase here back to my original size, so it's a little bigger. But, okay, so the derivative dy dx is the negative sine of x. Okay? So you can see it looks like sine, only it's reflected across the x-axis, right? So all the positive values are negative and the negative values are positive. Okay? So, all right, there we go. So now we have the derivatives of sine and cosine. And they're, so this is what you need to know. This is what you need to know. The derivative of sine is cosine. Derivative of cosine is the negative sine. All right, so now let's use that to do some to do some derivatives. All right, to differentiate some functions. So let's start with this one. All right, so here we have a function that is basically the difference of two trig functions, 5 sine of t minus 8 cosine of t. Now you're going to have to remember all the rules that you've learned previously about derivatives. So if you have a constant times a function, the derivative is going to be a constant times the derivative of the function. All right, so let's just do this. So the derivative of h of t is equal to 5 times the derivative of sine of t, which is cosine, okay, minus 8 times the derivative of sine of t, which is going to be negative sine of t. Okay. Now it'd probably be good to clean that up because I have a negative 8 times a negative sine t. So I can rewrite that as 5 cosine t plus 8 sine t. Okay, just because a negative times a negative is positive. All right, so here's another one. Y is equal to 5 minus 3 sine x plus x cubed. Okay, so again, the derivative, I'm going to write dy dx this time. Now the derivative of a constant is always 0. Okay, so you can imagine if you graphed a constant, you know, it's just a flat line, the slope is 0. So the derivative of a constant is 0. And then we're going to have negative 3 times the derivative of sine, which is cosine. And now we have to use the power rule to take the derivative of x cubed. So we're going to get 3x squared. All right, now these other examples, we're going to have to use some of the other rules that we learned, the other techniques that we learned in, what was that, chapter 8. Here we have the sine of t squared. So we've got an inside function and an outside function. All right, so so we're going to need the chain rule for that one. Let's write that down. Chain rule. We're going to have to use a chain rule. Now, I'm gonna do this a slow way just to make sure that you remember how to do the chain rule. I'm going to define the inside and outside functions, take the derivatives of those, and then apply the chain rule. Okay, so now I did post a derivatives review, and so if you're having difficulty with remembering how to do chain rule, product rule, quotient rule, and all of that, I recommend downloading the derivatives review and working on that. There's a summary of all of the rules that we've learned previously. All right, so, but I'm going to assume that you remember. And if you don't remember, you should do a little bit more work. All right, so I'm going to define the outside function. I'm just going to call it u. The outside function is just the sine of v, where v is equal to t squared. That's the inside function. Okay, now the derivative of u, du dv, with respect to v, okay, is the cosine of v, right? Derivative of the sine is the cosine. And the derivative of v, I'll call it dv dtt now, is going to be 2t. We're just using the power rule. So then we can put that all together using the chain rule. So g prime of t is equal to the derivative of the outside function with respect to v. So we have the cosine of v, which is, and v is t squared, so I'm just going to replace it with t squared, times the derivative of the inside function, 2t. Okay? That's all there is to it. All right, let's do another one. Here again, we're going to have to use the chain rule here. We've also have a constant multiplier. So, if I do this the slow way and break it down for you, u is equal to 5 cosine of v. That's the outside function, where v is equal to 2x. Then the derivative of the outside function is just going to be 5 times the negative sine of x. I'm going to put the negative out here. So it's negative 5 sine of v. The derivative of v is just going to be 2, right? Just using the power rule. And now we can write the derivative, f prime of x is equal to negative 5 sine of v, where v is 2x. Okay? And then times the derivative of the inside function, which is 2. So I could rewrite this. Might look a little nicer if I wrote it this way. Again, just as I told you in the chapter on derivatives, you do not have to simplify. This is a pretty easy simplification, so it's no big deal. But sometimes you feel compelled to simplify because it looks really ugly. But if you make mistakes, then you're like, suddenly it's wrong, and it's actually easier for me to check it if you don't simplify. So, but in this case, it looks much nicer to write negative 10 sine 2x. All right, now those two both involve the chain rule, right? Right, they both involve the chain rule. So let's take a look at the next one here. Here we have one that involves the product rule, because we have the product of two functions. We get the function t and we've got the function sine of t. So we have to apply the product rule on this one. Okay, so I have two functions. I'm just going to call u equals t. That's the first function, first factor. And I'm going to call v sine of t. Okay. And then I'm going to take the derivative of each one. Okay, the derivative of t is just 1, right? Again, using the power rule. The derivative of v is equal to cosine, right? Derivative of sine is cosine. All right, so now I need to use the product rule. Okay, so dA dt is equal to, okay, so I'm going to take the derivative of the first times the second. So 1 times sine of t plus the first times the derivative of the second. Okay? So that's just using the product rule. All right, we can also take derivatives of things that involve the quotient rule. We have a quotient of two functions here. So I'm going to use the quotient rule on this one. Okay. Now again, I've got two functions. I have a numerator and a denominator function. So I have high and low. So if you remember, it's low d high minus high d low, square the bottom, and away you go. So let's just write this out the slow way. Again, you don't have to write this out the slow way but if you feel if it helps you, then definitely do it. But sometimes it helps to sort of slow down and break it down, take it one step at a time. So I'm going to call u the numerator function, the high function, and the derivative of cosine is the negative sine. The denominator is t squared, right? It's my low function, and the derivative of that is 2t, just using the power rule. So the derivative, dr dt, is low, right? Low, which is t squared, d high, which is I'm going to put the minus out here, minus sine t minus high, which is cosine, d low, which is 2t, all over low squared. So t squared squared is t to the 4th power. And that's it. All right, got a couple more examples here. And so these two examples involve chaining the chain rule. Okay, so we're going to use the chain rule twice here. And the reason I say that is because I've got a square root function and which is the outside function, and the inside function is 1 plus sine t squared. And so we have another chain rule here because we have an outside function of sine and an inside function of t squared. So we're going to have to use the chain rule twice on this one. So again, I'll just take it slow. I'm going to call the outside function the square root of v, okay, where v is equal to 1 plus sine of t squared. Okay. So the derivative of u with respect to v is, okay, so remember this is equal to v to the 1/2 power. So I can use the power rule on it. So using the power rule, I get 1/2 v to the minus 1/2. Okay. Now dv dt, this is where I'm going to have to use the chain rule again. So the derivative of 1 is obviously 0. A derivative of cosine, derivative of sine is the cosine. So I get the cosine of t squared, but then I have to take it times the derivative of the inside function, which is 2t. Okay? So I've used the chain rule twice. All right, so let's put it all together. So I'm going to call it dp dt, and that's equal to 1/2, and I'm going to replace v with what v actually is, 1 plus sine of t squared, okay, to the minus 1/2. And then I have to take it times the derivative of the inside function, which is going to be, I'm going to switch these around. I'm going to write it 2t cosine of t squared. Okay? And that's it. You really don't have to do any more. I could rewrite this. Maybe make it look a little nicer. I can see that I can, 1/2 of 2 is just 1, so I could cancel those out. This is a negative 1/2, so I could put it in the denominator. Okay, I guess I'm going to do this because it's bugging me now. So we get cosine t squared, right? That's going to be our numerator. And because this is a negative exponent, I can flip it down to the bottom and make it positive, right? So it's going to be, and it's the square root, right? So it's the square root of 1 plus sine of t squared. Okay, there we go. Unnecessary steps. All right, let's do one more, and then I've got some practice problems for you to work on. Oh wait, no, I guess I have another one. I have one word problem. Okay, so let's do that too. But this is another example where we need to use the chain rule twice. So I'm going to just write that down. Chain rule times 2, right? Because we have a natural log function, and then inside is the cosine function, and inside that is this 3x to the 4th. So it's like a little Russian doll where we've got the inside of the inside is 3x to the 4th. And outside that you've got the cosine, and outside that you've got the natural log. All right, so let's do this. I'm just going to call u the outside function, natural log of v. Okay, du dv is just 1 over v, right? Now v is equal to the cosine of 3x to the 4th. Okay, and the derivative of that, now we have to use the chain rule. So I'm just going to take it the short way instead of trying to break it down again. But we have the derivative of the outside function, which is going to be the negative sine of 3x to the fourth, times the derivative of the inside function, which is just going to be 12x cubed. All right, now let's put this all together. So the derivative dz dx is equal to 1 over v, which is cosine of 3x to the fourth, times we have the negative sine, so we have the, and I might just flip these around just because I kind of like to have the 12x cubed out front. So I could just say minus 12x cubed sine of 3x to the fourth. Okay. And there you go. Now we could actually do some more simplification on this because I'm also seeing sine 3x to the fourth over cosine 3x to the fourth is tangent 3x to the fourth. So I could write this as, because essentially I could combine this so that 1 times negative 12x cubed sine of 3x to the fourth is all essentially the numerator. Okay, so I could write this as negative 12x cubed, and then sine over cosine is tangent, so I would have tangent of 3x to the fourth. Okay, again, that's not necessary in this particular case, but I just kind of like that. Makes it look much nicer, right? Doesn't that look pretty? All right, let's do the word problem. Okay, so we have in this word problem, we have, this is on July 7th, 2009. There was a full moon in the Eastern time zone. If t is the number of days since July 7th, the percent of the moon illuminated can be represented by this function. Okay, so the illumination of the moon is a periodic function, right? So, and it makes sense because things are moving in circular or near circular paths, maybe elliptical, but near circular ellipses. All right, so first of all, just ask us to find the derivative of this function h. Okay, so let's just do that. H prime of t is equal to, derivative of a constant is 0. Okay, so then we have 50. Derivative of cosine is the negative sine. So I'm going to put the negative out here. Sine of pi over 15t. But don't forget to use the chain rule here because this is an inside function right here. So we're going to have to take the derivative of pi over 15t. Okay, and to do that, we're just going to use the power rule. And what we end up with is pi over 15. Okay, so we had to use the chain rule on this one because it's not just t, it's pi over 15t. All right, so we can simplify that a little bit because I can divide this by 5 and get 10. I can divide this by 5 and get 3. So I could rewrite that as minus 10. I'm going to bring the pi out over here to the front. Pi over 3 sine of pi over 15t. Okay, so now we've taken the derivative. Now it's asking us to sketch a graph of the derivative h prime of t between 0 and 30. Now, whenever I'm asked to sketch a graph, I like to break it down a little bit. Let's think about what's the midline, what's the amplitude, what's the period, and also is there any horizontal shift going on, any phase shift? Now you can see the midline. I don't have a constant. I have this equation for the derivative. There's no constant added onto, so the midline is just y equals 0. The amplitude I can just read from the coefficient, this coefficient out front, right? This one right here. And so the amplitude is just 10 pi over 3. and the period. Now we have to find the period. So remember, period is 2 pi over b. So I get 2 pi over 15. Let's see if I can write that. Pi over 15. Okay. And when I simplify that, my pi's will cancel, and it's the reciprocal of the reciprocal of this 15. So we end up with 30 days. Right? The period is in this case, because t is in days, my period is in days. Okay, so our period is 30 days. All right, so let's try and sketch this graph. So I didn't provide any axes for you. You're just going to have to sketch it freehand. And I'm graphing it from 0 to 30, so I'm not going to worry about any negative values. So let's draw the axes. And so the period is 30 days. I'm going to start by just marking 30 days here. And right in the middle is 15. And then in the middle of that is 7.5. And in the middle of this is 22.5. Okay, I like to break it up into 4 parts because I'm graphing sine. And I know that the sine is going to start out. Now, again, it's a negative sign, though, so be careful of that. But either way, whether the 0 points don't change, right? So it's going to cross the x-axis at 0, 15, and 30. So once we have those 0 points drawn, now it's negative sign. So instead of going up and then back down, it's going to go down first. Okay, so it's going to look something like this, where it's going to go down to negative 10 pi over 3. Okay, and then it's going to go up and down. And it's going to go up as far as 10 pi over 3. Okay, so that's essentially what our h prime of t looks like. It looks really messy, but so oops, there we go. All right. So there's a sketch of our function for the derivative of the illumination of the moon. Okay, and that's telling us how the illumination is changing over time. Okay, so keep that in mind. Now, let's scroll down here a little more. So the next thing we're asked to do is for t between 0 and 30, when is the derivative negative? When is it positive? And what do these negative and positive values tell us about the moon? All right, so let's take a look at, first of all, where h prime of t is negative. Okay, so it's negative right here. Let me just mark it with red here. All right, so we're negative here. So the derivative is negative, which means it's decreasing, right? The illumination is decreasing because the h function was the illumination of the moon, and the derivative tells us how that illumination is changing. Okay, so the derivative is negative between 0 and 15. So 0, oops, and I shouldn't put less than or equal to, because essentially at 0, it's neither negative or positive. So I'm actually going to just erase that. All right, because it doesn't include 0. All right, so between 0 and 15, the derivative is negative, which means that the percent of the moon illuminated is decreasing during that time period. Okay, so let me write that down because we're asked to explain what we mean. So the percent of the moon illuminated is decreasing. during this time period. Okay, which makes sense because we were told in the original problem statement that the new moon occurred on July 7th, right? And so, or sorry, the full moon occurred on July 7th, and so after the full moon, the percent illuminated is going to decrease from there. So that makes sense. Okay, so now let's look at where h or the derivative is positive. I can't write here. Positive. Okay, so you can see, I'll mark it, let's see, use a different color. Let's mark it with blue. So this, ooh, that's purple. That's weird. Okay, actually, I'm going to try a different pen. Okay, this part up here. This part up here is positive, right? Okay, so between 15 and 30, so 15, whoops, 15, I can't write today. All right, 15, between 15 and 30, the derivative is positive, right? So that's telling us that the percent of the moon illuminated is increasing. Okay, so the percent of the moon illuminated is increasing during this time period. Okay, I'll just go ahead and write it all out. During this time period. Okay, increasing when it's positive, decreasing when it's negative. All right, so finally we're asked for the time period between 0 and 30. When is the derivative equal to 0? Okay, so the derivative is equal to 0. You can scroll back up to our sketch, right? It's equal to 0 at 0, 15, and 30. Okay, so let me write that down. H prime of t equals 0 at t equals 0, 15, and 30 days, right? Because our time is in days. Okay, so what's that telling us? That anytime you're crossing, anytime you're crossing 0, well, in this case, we're going from increasing to decreasing, or decreasing to increasing, right? In this case, so essentially, what that's telling us is that at t equals 0 and 30, those are the times when we're going from positive, and then you can see we would eventually go negative here, or like here we're going from positive to negative, Okay, so the percent of the moon. Let's see, the percent of the moon illuminated illuminated, I can't spell, illuminated, it goes from increasing to decreasing, okay? Goes from increasing, so it's positive, increasing, to decreasing. Okay, so if you think about it, so the problem said that on July 7th, which was our time t equals 0, we had a full moon, right? So it makes sense that, prior to that full moon, the illumination was increasing, right? And after the full moon, the illumination is decreasing. So this corresponds to a full moon. These are the periods where we're going to get the full moon. Right? Now, the flip side of that, when at t equals 15, you can see we're going from decreasing to increasing. Okay, so if we were to interpret that, we could say that at t equals 15, the percent of the moon illuminated goes from decreasing to increasing, right? So what does that mean? The percent of illumination goes down, 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 down until it's basically dark, and then it starts increasing. So this corresponds to a new moon. Okay, this is the case where you get where the moon is totally dark. Okay, so it can't decrease anymore, and from there it just starts increasing until you get to a full moon again. All right, now there's some practice problems here. The solutions are in the completed lecture notes, so I'm not going to go through all of these problems here, but you can look at, I want you to do them and then check your answers with the completed lecture notes. All right,